Okay, here we go. Now we're going to look into electrical basics. This is mostly for students that are beginning in Intro to Automation and have not completed the electrical applications course. This is definitely not going to cover everything that is covered in electrical applications. It's just going to get you what you need to know to be a first-time student in Intro to Automation. So in this lesson, we're going to have some objectives. We want to be able to define the concept of voltage and how to measure it. Same for current, resistance, and we want to understand the concept of power, and I'll explain why I don't show you how to measure that. We want to be able to compare an open circuit versus a completed circuit, and we want to be able to contrast a series circuit to that of a parallel circuit. Okay, let's get going. So electricity comes in two basic forms. We have alternating current, AC, and we're going to dive into each one of these types, and direct current, DC. Okay, so we basically have those two forms. Now when you get into AC, there's multiple forms of AC, whether it's single phase, split phase, three phase. Direct current is pretty much just direct current. Okay, for alternating current is useful, and is why we use it at home, is because we can transmit it over long distances with minimal losses. And the electricity that we use out of the outlet in our home is alternating current. Of course, in commercial buildings as well as industrial applications, we also use alternating current. In industrial applications, it is three phase instead of single phase. I'll show you what single phase is in this presentation. And the name alternating current is derived from how it actually presents itself. We're going to see in the next slide what alternating current actually looks like. But the current flows in one direction for a given amount of time, and then it flows in the opposite direction, or it alternates around zero for the same amount of time. And a typical wall outlet, we get 120 volts, and it's single phase. You're going to see a graph of that here in just a minute of alternating current. So to the left is a generator. We're going to learn about that in electrical applications. But to the right is what we call a sine wave, or a sinusoidal wave. And if you ever studied trigonometry, their sine, cosine, and tangent functions all have to do with this mathematical principle. But what we're looking at here is a sine wave. And if you notice, it's alternating. That center line here in the middle is 0 volts. Or amps, I guess, 0 amps. Up here would be the maximum amount of amperage in the positive direction, and down here would be the maximum amount of amperage in the negative direction. If you notice, it continues to alternate back and forth. And this is going to be very useful for us for transforming the power and transmitting the power, and that's why we use alternating current. So that just gives you a visual of what we're talking about when we mean alternating current. Conversely, direct current is useful because it can be stored in a battery. It doesn't have to be. We could transform through a power supply alternating current into direct current. In fact, the power pack for your computer does that. We plug it into the wall, and it goes through that little box that has a transformer and some other electronics in it to convert it from alternating current to direct current. And ultimately, your computer runs on direct current because we can, if it's a laptop, we can unplug it and walk around and still have it powered by an internal battery. DC electric power can be found in cars, cell phones, personal computers. Pretty much anything that doesn't have a cord that connects to a wall is going to have, and is electronic, is going to have a direct current or DC battery in it. The name direct current is derived from how it presents itself. The current flows in one direction continuously. It does not alternate. We're going to look at that on a graph as well. And the typical car battery has 12 volts of potential available to start the car. Some cars, older cars, worked off of 6 volts. Some motorcycles work off of different voltages. And some boats work off of different voltages as well. So this is what direct current would look like. This is the same graph, but it doesn't alternate at all. It's just steady. It is a constant current that we get out of this battery, and that's why it is called direct current. It doesn't alternate. It is just a direct signal. That's why it's a straight line. Okay, let's look at the concept of voltage. Okay, voltage can be thought of as electrical pressure. So I like to compare electricity to water pressure, because a lot of people understand water pressure. When you are at a sink and the faucets are closed, there's a certain amount of pressure that's available to you. You just can't get it out of the faucet till you actually allow a path for that water to flow. But that pressure is there, and that's what we have in a battery as well. It's electrical pressure. It's available to us. It's not being used. This battery right here is not being used at the time. It is, but it has a certain voltage that is available to us. So water in a faucet has pressure, potential energy that needs a path for the water to flow. Same for a battery. Battery has voltage, which is potential energy as well, that is ready to use, but it needs a path. Okay. The source is measured in volts, which is abbreviated by the letter V. So those are the units. And in this picture, everybody's pretty familiar with this. This is a 9-volt battery. So it has 9 volts of potential energy. But currently, if it's not in a circuit, that energy isn't being used. It's just being stored. Let's look how we would measure voltage. So first, we know that there's 2 different types of electricity: alternating current and direct current. So we need to make sure that we're selecting the right selection when we turn our meters on here. Now it kind of makes sense. The V stand for voltage, and then the squiggly line over the top is meant to depict a sine wave, which is alternating current. So the V with a straight line over it is our direct current. Okay, it does not alternate. So when we're measuring from a battery, make sure to click it to this second position right here. And when we're doing alternating current, make sure to select that position there. Okay. When we measure current, the black lead goes there. As a matter of fact, the black lead always goes there for any measurement. And the red lead would go there for voltage. You can see right here it says V. So for voltage, you put the red lead there. It's not always going to be that location for all measurements. And then we want to ensure that we have the right units here. So if you click it to this first position, we're measuring AC. Make sure that it says VAC, volts AC here. If you click it to the DC, it may still say VAC, and you have to push this yellow button here to switch that to DC. So just keep an eye out for that. Okay, now let's talk about current. Current can be thought of as electrical flow. Okay, so water from a faucet flows when a path is given to it. Okay. The battery produces current when it has a completed circuit provided to it. Okay, so conventional current flows from the positive terminal of the battery to the negative terminal. There's actually another way of looking at current, but in this course, we're always going to refer to current flow as conventional current flow, and that is positive to negative. And current is measured in amperes, which we just shorten as amps, and it is abbreviated with the letter A behind any given quantity that you have. So let's look at a completed circuit here. So this is the internal workings of at least an older style conventional flashlight. Now they have LEDs in them. But this would be 2 C cells or D cell batteries that you would put inside a flashlight, and they're stacked on top of each other. And the positive is on this end and the negative is on that end. If you notice, the positive of this battery connects to the negative there. So we're stacking them on top of each other. And we're going to learn later that's going to double the voltage here. So each one of these is 1.5 volts. So this is 3 volts of potential energy. And so this light bulb that we put across here needs to be a 3-volt light bulb. So this is the old incandescent bulb type. And this is where we're going to put the positive terminal, and then the negative connects on this outer shell. This is one side of the black bump here is one side of the light bulb, and the silver outer shell is the other side of the light bulb. And we're connecting that through a switch. This is a knife switch. It literally looks like a knife chopping into a block of two prongs that will make a physical connection when we push down on that lever. But when it's open, you notice there's an air gap here. There is no connection. This is a wire that connects to this screw terminal. There's no electrical connection between those screw terminals. The only way it would happen is through this knife switch, and then this screw terminal is connected to the negative of the battery. So currently the switch is open, so we do not have a completed circuit, and that equals that we have no current. Okay, so here now we have closed the switch. If you notice, this screw terminal is connected to this screw terminal. This color is to depict that this is copper, and so those are copper metal components touching each other. And now that that is closed, we have electrical current. And since we're studying conventional current in this course, we are going to come out of the positive through the light bulb, and once we're flowed through the light bulb, we're going to come through this wire through our switch and then down to the negative of our battery. And it's actually like a racetrack. It just keeps going around and around. The current just keeps flowing in a circle. Okay, so that is our current that is direct current. It goes in just one direction, and conventional current flows from positive to negative. And this is happening because that switch is closed. And when that switch is closed, the term that we use is it's a completed circuit. Okay, and when we have a complete circuit, then we'll have current flowing. Okay, let's look how we're going to measure current. Okay, so there are two settings for current. Now you would think, one's for AC and one's for DC. No, actually we're going to measure current either low amperage current or high amperage current. Okay, so this first selection right here, all the way over here, is for currents that are less than 0.4 amps or 400 milliamps. And we'll when we get into electrical applications, we'll be able to quantify how much current that actually is. So if we're measuring smaller currents, we're going to use that setting. And if we're using larger currents, larger than that 0.4 amps, we're going to select the second one there. If you're measuring AC current or DC current, you're going to use, if it's AC or DC current less than 4 milliamps, you're going to use this setting right here. Okay, the lower one. And if it's AC or DC for the second one, you're going to use that one right there. Okay. Make sure when you set it that your setting is for the proper electricity that you're measuring, whether it's AC or DC. And again, you'll just push this yellow button that will change that from AC to DC for you. Black lead goes there. It always goes there. For the lower currents, it's going to go in the one that says 400 milliamps. 400 milliamps is the same as 0.4 amps. If it is higher than 400 milliamps, we're going to use this lower one, which is protected up to 10 amps. So that's why we have two separate fuses inside our meter as well. Okay, let's look at resistance. Resistance is the opposition to electrical flow. And when water throws through a pipe, resistance can be found in obstructions in the pipe, like a reduction in the pipe, which we're kind of showing here in this picture, or a filter in line. So imagine a garden hose has water running through it. If you start squeezing the garden hose and causing a restriction there, you're going to slow down the water flowing through it. So this is a really good depiction right here in the lower right hand corner of a volt, an amp, and an ohm. It really kind of pictorially gives a description of what I'm showing you. Voltage is the pressure that is pushing the amperage through the wire, and ohms is what is restricting how much how much flow you're going to get through the wire. Okay, but they're depicting it like a pipe here. Every conducting material, even copper, has some quantity of resistance. Now copper The resistance of copper is very, very low. That's why it makes a very good conductor. But it has to have some form of resistance for there to be electrical flow. If it has infinite resistance, then it is an insulator, which is what we put on the outside of the wire to insulate us from getting shocked. Every circuit needs resistance in order not to damage the power supply. Okay, so even though copper does have some resistance, if I hooked a copper wire from one lead of your car battery to another lead of your car battery, because the resistance is so low, the amperage would be so high and it would damage the battery. So we need an appropriate amount of resistance for the power source. And typically we either use a circuit breaker or a fuse to protect the power source to make sure that we're not going to try to draw too many amps out of it. And then the fuse will blow or the circuit breaker will pop, and you'll have to reset the circuit breaker or replace the fuse if that occurs. The resistance is measured in ohms, which is the Greek letter omega is what we're going to use to represent that. Ohm is the gentleman who actually discovered the concept of the electrical resistance, and that's why the units were named after him. Okay, let's see how we're going to measure resistance. Okay, so to measure resistance, if you notice, that ohm symbol is right there on the meter. So the omega symbol, that is going to represent ohms. So you select that to actually measure a quantity. And so then you want to ensure that it says ohms there. The picture that I have for this meter was it only showed volts there. So don't be confused that we're talking about ohms and this says volts up there. That would say ohms up there. Black lead goes in the lower right-hand corner, and the red lead, again, goes over here in this position. If you notice, the omega symbol is also shown there. Okay, let's talk about the concept of power. So power can be thought of as the rate of electrical energy. In fact, you know, when you pay your electric bill, you pay a certain rate. You're paying your power bill because it's the rate of electricity that's coming into your house. And if you're using more electricity, the rate increases. That's why you pay more for your electrical bill than maybe your neighbor who has a slower rate coming into their house. One way to understand power is through heat. So an incandescent light bulb, when lit, produces light and heat. Both of those are forms of power. Okay, so when we power up a light bulb, we use that term a lot. You power up the light bulb, it is producing light. And an incandescent light bulb, I specifically say an incandescent light bulb, it's actually very inefficient. That's why we replaced it with compact fluorescence and now LED bulbs, because they produce light without producing much heat. The old incandescent light bulb produced light and a lot of heat. In fact, you would burn your hand if you touched the light bulb. Now, if you touch a light bulb, it's so cool that it doesn't actually hurt. Power is measured in watts, which is abbreviated by using the letter W. So now all of the wattages that people are used to, like a 60-watt light bulb is the common one that we would use around the house. When you buy LED light bulbs now, they'll say it's a 60-watt equivalent. It actually draws considerably less wattage to produce the same amount of candle power that a 60-watt incandescent light bulb would be. So if you go out and buy a 120-watt LED light bulb or equivalent light bulb, it's probably only going to pull something like 10 watts, which is why it's an energy saver. So a 60-watt incandescent light bulb, I'm very specific to say incandescent light bulb, will consume 60 watts of power. Okay? We cannot measure power with our meter. Okay? There are meters that you can do it. It actually takes extra leads to be able to do it and take two measurements at the same time. But it is possible for us to calculate active power by multiplying the voltage across a component, the current through it, and doing this calculation. Watts is just going to be volts times our amps. The meter that I spoke of would actually be a meter that you could take a voltage measurement and a amperage measurement at the same time, and then internally inside the meter it does the math for you. But our meter doesn't do that. But it is possible for us to calculate it anyway. Let's look at some electrical symbols. We don't physically draw a battery on the screen. Batteries come in different forms and shapes. So this is the modern version. There are some archived versions of being able to depict the battery, but in our study, we're always going to use this modern representation. It's a circle with a plus and a minus. We use the circle because quite often batteries are round, like a D cell or a C cell, or even the little ones you put in watches and things like that. And then we just show a positive and a negative, typically positive on the top and negative on the bottom. And then we say what voltage that power source is. And for a 9-volt battery, we would put 9 volts to the left of the circle there. For an alternating current signal, we actually replace the plus and the minus inside the circle with a sine wave. So that makes sense because we saw that alternating current presents itself in a sine wave form. And then we just write 120 volts on the outside. Now, we don't actually have to put 120 VAC to denote that it is AC when we use the symbol, because the symbol tells us AC or DC. When we actually write it in a sentence, we do need to actually say 120 volts AC, just so people know we're talking about AC and not DC voltage. A resistor, we haven't really messed with resistors yet, but what is depicted there to the left is a resistor, and you're going to get a kit in your lab bag that will have a whole set of these resistors. And then the resistors have a color code, and so that particular resistor is a 4.7 k ohm resistor. The symbol to the right, showing the squiggly line, is much like a path that you would have to walk that would slow us down. If we ran in a straight line, it would be a lot faster than if we ran zigzag. So that's supposed to mean that the current has to go through this zigzag pattern, some sort of resistance, and that's where the symbol came about there. When we use the term open circuit, this is to depict that knife switch. This is just a generic switch, but that knife switch that I was showing on the flashlight example is depicted by that symbol, and the switch is open right now. So we currently don't have any current flow because we have an open circuit. If we close that, now you can see that the gate or the door has been closed there. We do have a path for current to flow. So now we have a completed circuit. So I just want to differentiate the open circuit versus the completed circuit and how those would look to us. Okay, when we have multiple components, we have a couple options of how we can wire them up. If two components are to be incorporated in a circuit, there are two possible connections. You can connect them in series, and we'll see a picture of that, and you can connect them in parallel. And those are the only two options if you have two components. So series connected components would be depicted like this. This would be a 9-volt battery and those two resistors that we have. We would take the 9-volt battery, we would connect it to one end of the resistor, and then the opposite end of that first resistor we would connect to the beginning of the second resistor, and then the end of that second resistor would be connected back to our 9-volt battery. That is connection in series. And over here, we would connect the beginning of the 9-volt battery to the beginning of both the first resistor and the second resistor. And then the ends of each one of those resistors would get returned to the negative of the 9-volt battery. And that would be connecting those components in parallel. Let's look at the characteristics of series and parallel circuits. So in a series circuit, the current is common. Okay, so the current that flows through resistor 1, the first resistor, is going to flow through resistor 2 as well. Okay, but the voltage is going to be divided up. So there's going to be a certain voltage drop, and in the electrical applications course, we'll go into all the formulas of how to calculate that. We're just doing an overview here. The voltage gets divided amongst those components. And the resistance, when you add resistance onto this circuit, it's going to increase our total resistance. And the power consumed by each one of the devices is just additive. So we can just add them all up to get to our total power. Okay, so conversely, let's look at the parallel circuit characteristics. Voltage is common among the two. Okay, so the current is no longer going to be common, but the voltage is going to be common. Remember, if we look at the picture, it's going to have those components both connected across the power supply. So in this picture back here, this 9-volt power supply, we're going to have 9 volts across this resistor, and we're going to have 9 volts across this resistor. Conversely, over here, we have 9 volts here. Well, that 9 volts has to be shared across 2 resistors, and because these resistors are of the same size, we're actually going to have 4.5 volts across this resistor, and we're going to have 4.5 volts across that resistor. Reason being, they're both the same size. So it's going to divide it evenly. If this one was smaller than that one, that wouldn't be the case. Okay, so you can see here, the current that flows through here is going to be the same. There's no other path for the current to take, where here I have 2 paths for the current to take. Here the voltage has to be divided, but over here the voltage is not divided, it's shared among the two, but the current that flows through this wire is part of it's going to go through this way. In fact, as a matter of fact, because they're the same size, half the current's going to go this way and half the current's going to come that way, and then they're going to join back over when it returns to the battery. Okay, so the current is divided among those components. Adding a resistor in parallel is actually going to decrease your total resistance. And that's going to make sense when we think about it. You add more resistors in parallel, you are going to increase the amount of current load. So that means if you're increasing the current load, the resistance would have to decrease. So the best example of this is Christmas lights. If you plug in your Christmas lights and then you keep plugging Christmas lights in the end of that, you're going to, because all those lights are in parallel, you're going to keep adding more current onto that, and you're actually going to, they actually put little inline fuses in your Christmas lights now. If you add too many lights in a row, you're going to draw too much current for the wire size, and you're going to pop a fuse in your Christmas lights. But the power consumption is additive. So that's the only thing that's common among the two, between series and parallel, is power still adds up. Okay. So that is a quick overview of electrical and the terms that we're probably going to be using this semester. You'll hear me throwing out in Intro to Automation. I hope that helps, and we'll see you in the next video.